me know when we're streaming.
Okay, I'll go ahead and start stream and let you know.
Okay.
Okay, we're live.
Hi, everyone. Welcome to the April 2020 edition of Wikimedia Technical Talks. The Technical Talks is a monthly series where speakers share their knowledge of technology used on Wikimedia projects. Members of the community are encouraged to propose talks and participate. And you can learn more about these talks on the MediaWiki.org page, which is linked to the description from YouTube. Today's speaker is Lars Wirzenius, a senior software engineer at the Wikimedia Foundation. Please feel free to share questions for Lars through the YouTube live stream and through IRC on the Wikimedia staff channel. When Lars is finished with his talk, I'll share your questions with him. If there's a question that we can't get to or need more context for, we'll follow up with you after the talk. So without further ado, I'll hand it over to Lars.
Hello. I will start by saying a couple of words of myself. I've been working at the foundation for a little over a year. I am not an expert on cryptography, which, considering the topic of the talk, is a little bit of a surprise. But I've been playing with PGP and related technologies since 1995. And for a little while, I maintained PGP, the package in Debian in the mid-90s. But without anything else, the goal of this talk is to talk about why cryptography is important and how does it work, at least conceptually, if not with deep math. The math thing is the one I don't really know. To me, it's magic, but I can go through that for myself if I need be, but I don't want to confuse other people. And then a little more specifics on how to use these tools, and then follow-ups. So why would anyone attack any special person, any particular person in the current audience? And the division is usually that you might be important. You might be the president of Russia, and that's important. Or you might have important data. You might work for the Wikimedia Foundation and need to have on your computer some personal information about people who use Wikipedia. And the government of China might be interested in that. Or you might have a really powerful laptop and someone might want to use that remotely. Or it might be that you're not important, but someone might want to get to someone else via you. So for example, if your boss, if the foundation ED, Catherine, trusts you and believes everything you say, then you become much more valuable as a target. Or it might just be that you're an easy target. I know how that feels. And there are various ways of doing attacks. An attacker might pretend to be you, or might pretend to be someone else to you. Impersonation is the word. They might falsify files that people download. So the MediaWiki Turbo release, for example, which is used by NASA. And if NASA is an interesting target, then tampering with the MediaWiki Turbo release is a way to attack them. Or it might be that someone just wants to eavesdrop. And I'm sure there are other attacks, but those will do. There are all sorts of attackers or potential attackers. There might be governments, law enforcement or espionage organizations in any country, not necessarily your own. There might be a large private organization, like, say, a huge multinational corporation. It might be a criminal organization and so on. Or it might just be that someone has too much time. And one of the primary defenses here is then cryptography, especially widespread use of cryptography, so that you don't stand out when you use cryptography. And the most common example of that today is HTTPS, which is now almost everywhere, and it is considered bad form for a website to not provide its contents over HTTPS. Apart from cryptography, there's also other tools that can be used, and training to use them and do things. The words infosec and opsec are used here, so related and in general good habits. All the things you've ever seen in a spy movie apply. Although sometimes they apply in the reverse, so don't do the things that spies do in the movies. Security is difficult. Perfect security seems to be a fantasy, but there are levels that are important. And I like to compare this with driving a car. So if you just need a car so you can go to the grocery store and buy food, although that might be a bad example right now. But for driving for errands, you need different kind of driving than if you drive for Formula 1. And you can't even sit in a Formula 1 car until you've gone through a whole bunch of driving training. And the problem with all of this is that if the attacker is sufficiently motivated or well-funded, they will win. And that's not good news for anyone. So everyday uses of cryptography is it sounds like something that only spies in movies care about, although cryptography in movies tends to be a really bad thing. They always get it completely wrong. I tend to sign all my email, especially personal email, not because I'm a particularly valuable target, but I think it's a good habit to have. I occasionally encrypt important email about things that is not supposed to leak. Those tend to be very personal issues, either for me or for the other party. I sign Git tags so that the release is fixed and it cannot be modified and it cannot be falsified. I sometimes sign commits as well. That would be something that I think would be good for more people to do. Software releases should be signed so that downloads can be verified. So modern cryptography has knows two kinds of cryptography. There's symmetric, which is the traditional one, and asymmetric, also known as public key cryptography, which is the new invention. In symmetric encryption, you have one key and you both encrypt and decrypt with the same key. So the secret stays secret only as long as you share the key. And this is very, very strong, except how do you transfer the key to the other party? Say I make a turbo release of MediaWiki and I crypt that with a symmetric encryption key, and anyone who has that key can verify that my file is correct. But if they have they need the key to decrypt that, but if they have that key, they can make their own turbo release, and then there's no security. So that's not good. In asymmetric encryption, there are two keys, and they are linked. And they are linked so that if you encrypt with one key, you can only decrypt with the other key, and vice versa. So the same key that you use for encryption cannot be used for decryption. And this is called public key encryption because one of those keys is usually called the public key, and the other one is the secret key. And the idea is that anyone can have a copy of the public key. So if I want to make and only I have a copy of my secret key. And if I make that tarball release, I will sign it with my secret key, and I will publish the tarball and the signature. And anyone who has my public key can verify the signature, but they can't make a new signature. So it's the so-called key distribution problem is much, much simpler. The public key cryptography was first publicly invented in 1977. That's not a very long time ago. I was in school by then. It was supposedly not the first invention of that technology. The British encryption people invented it in the 1950s, but they decided it's too useful for them to ever tell anyone. So they don't really get the credit. The invention of the RSA algorithm in 1977 and the publication of that basically started the non-government cryptography research, and the whole field exploded in the late 70s, early 80s. And it happened that in 1991, someone who was concerned about, I think, anti-nuclear demonstrations wrote a program called Pretty Good Privacy, or PGP. And that was the first implementation of public key cryptography that was popular and freely usable by anyone. I'm sure there were other implementations, but those weren't really popular. And PGP then caused another explosion in popularity. And throughout the 90s, the US government especially, but also other governments, wanted to combat this. They did not like people having secrets. They tried to do this by, for example, having export restrictions on cryptography. Very early in the 90s, they were supposedly worried that the Soviet Union would have encryption. But not getting into that now. It's a long story. But basically from the early 90s, the United States wanted to curtail the use of encryption. But even so, encryption is so useful and so important that people started using it anyway. In 1995, the secure shell, or SSH, and the secure socket layer, or SSL, were both first launched. These allow strong encryption, the public key encryption, to be used across network connections. And now the crypto wars got worse. And the US export restrictions meant that you could have encryption and you could export encryption, but the exported encryption should be so weak that the US could break it. And if the US can break it, then basically anyone else can as well, anyone with a bit of money. This did not stop crypto from becoming more and more popular. And some of you may have heard of the mobile phones encrypt their data now. And iPhones have been using that for a little longer. And the FBI keeps saying that they can't combat crime at all because criminals use iPhones and they can't open those. So we are now living in the second crypto wars. So SSH and HTTPS are used everywhere. anyone who administers Unix machines, Unix servers, uses SSH. All the other ways of doing that are so insecure that nobody wants to use them anymore. These are for transfers, so we call it data in transit. So while data moves across the internet, nobody can read that. They do not, however, guarantee that the data you get over HTTPS is what the person who put it available on the web meant you to have. Because if the server that serves the page or this file, if that's breached, someone breaks in there, then HTTPS cannot guarantee that the data hasn't been tampered with before it's sent over HTTPS. For that, PGP is still one of the most popular tools. As it happens, the original PGP software was sold and bought and multiple times, and it became proprietary, no longer free to use. So free software hackers wrote a version called GnuPG from scratch, and it basically has replaced the original PGP entirely. But because interoperability is important, they then also wrote a standard called OpenPGP, of which GnuPG is just one implementation, although the most popular one. And there are versions of the OpenPGP standard implementations for all popular computer operating systems and possibly mobile phone systems as well. I haven't actually checked. And PGP is good for data at rest. It's also good for transfer. So if you encrypt the file, you can transfer the encrypted file over a non-encrypted channel. But more importantly, even if you use HTTPS for transferring the file, the PGP signature verifies that it hasn't been tampered with. I will now do a demo, which will traditionally break. As soon as I figure out how to use Zoom. Okay. And then I will switch to my other window. That should look like a thermal window. Can someone confirm in chat?
Yes.
Thank you. So the first thing I will demo is I will show how to generate a PGP key with GnuPG. I have the software is installed. This is a Debian system, since I'm a geek and I don't use Mac or Windows. But that's the command. This generates a new key using a quick approach, so it asks fewer questions for a made-up name with a real email address, and I'll get back to why the made-up name is important. And then I say yes, it should do that. Everyone please look away, I'm writing my password. Okay, that did not work. Okay, so now it generates a key. I have a key, and this command will, the capital K option, shows the private key, tells me that I have a key. This part the long hexadecimal number is called the fingerprint. That's the best identifier for the key. And the other part, it tells me the algorithm and key size, and when it was created and when it expires. I'm going to ignore all of that for now. The important bit is that we have a key. And then you may notice that I was able to set a name that I chose. As far as I know, there is no person of that name. So GPG has no way of making sure that this key is this name person actually exists. And this downloads my actual key. Which looks like gibberish, which is intentional. The key as such is not meant to be human readable. And then I'm importing it. GPG maintains a key ring, as it's called. And one can import other people's public keys to the key ring with that command. You don't need to make note of all these commands. There are excellent tutorials all around the internet. So I have imported the key, and it tells me that someone called Lars Wirzenius has that key. And then I can list all the keys I have. This lists all the public keys. Dash capital K lists all the secret keys. So there's one with the one I just created, and this is my other key. And the interesting part here then is that how do you know that which key belongs to which person? Since anyone can create a key and they can put in any person's name, any name they want there, also any email address, GPG has no way of checking that. There is a procedure called signing keys or certifying keys. And that means that I can ask these Laurentius persons, I can verify that this key, which is my real key, belongs to this person, and I, as Laurentius, certify that this is so. And then anyone who knows Laurentius and trusts them to be honest can trust the key. And if anyone actually knows Laurentius and thinks they're honest, I have a bridge to tell you. And one can sign, so any key can be associated with any number of names. I don't want to sign all of those, so I will only sign my Wikimedia address. And then I sign it, and it tells me the fingerprint, which I should verify very carefully, and the name and email address, which I should also verify carefully. So I, as Laurentius, should go and meet this Lars person and verify in person or in some other way that the fingerprint is theirs, and also verify their identity. And this can be done in various ways. And the important bit is that I, as Laurentius, need to be convinced that this person is the person they claim to be. And yes, I'm very convinced that that is the person. And I have signed the key, and then I will save it. And if I list the signatures, I can see that Laurentius has actually signed that key now, which is nice of Laurentius, very trustworthy. But now Laurentius has a signature locally. And that's fine, except it's not of no use for anyone else. So what happens then is that Laurentius exports the key from, sorry, I am missing a step here from my notes. So let's go back. So Laurentius exports the key from the keyring into a file. And this is what it looks like. It has some information saying it's a public key, and then a lot of gibberish. We don't need to care about that. And then the idea is that Laurentius encrypts this file, which has Laurentius' signature on Lars's key. And then like that, and we have this is the encrypted file, says PGP message, and I have no way of decrypting this unless I have one of those secret keys. It has been encrypted for Lars and for Laurentius. So if Laurentius does this, they can see the public key block. An encrypted message can be encrypted to any number of recipients, which is very handy if you want to talk to many people. But so we have an encrypted message, the ASC file at the end. And if we give this file to Lars in some way, then only if Lars, so basically if we email this to Lars, then this verifies that the email address also works. If Lars can decrypt the message sent to their email address, then clearly the address works. However, since I don't want to actually go via email, I'm going to pretend that that can be done. I just copy the file somewhere where Lars can find it. And then let's see if Lars can actually find it. Yes, Lars can decrypt the message. Excellent. So Lars can then sorry, I'm copy pasting from another window and we will come in. So the first part of this command decrypts the message, and then it feeds that decrypted message to GPG import so that the signature can be imported. And yes, we imported one new signature. So the idea is that Laurentius needs to sign every email address of Lars's and send it separately to each of them. And if this verifies that all those email addresses work. If that sounds like a lot of work, you are entirely correct. Luckily, there is tooling to help. Let's try something else. Let's create a secret message and sign, not encrypt, but sign that with clear signing. And it looks like this. This is a secret message. And if we copy that file to the temporary directory so that Lars can see that, then this is a secret message. And there's no, cannot check the signature because there's no public key. So what we do is we export our end user key. Oops, that was not what I meant to do. This copy pasting thing is difficult. That's the public key. Import the public key. Then we decrypt the message again. And now we have a good signature. Since Lars has not signed Wirzenius' key, GPG doesn't fully trust the signature because it can't verify the identity. It can't verify that the identity is trusted, but it tells you that the secret message is there. However, if someone modifies the message while it's in transit, so a perfectly reasonable message, and it has a lot of PGP gibberish around it, so it must be valid. However, if the recipient does this, PGP will tell me that the signature is bad because I modified the message without generating a new signature, and therefore I can't trust the message. This is a different case from I can't, that signature is good, but I can't trust the identity. So that's a thing that needs to be able to be done so that communication over the internet is not vulnerable to attackers, especially attackers who want you to change the passwords. That was a quick demo. So the next thing you should do is make a key if you don't already have one, and then get it signed by your coworkers or other people using PGP. I'm not going to go through all the steps in extreme detail because there are guides online. There are 2 links on those PDFs if you want to try those. And if you have trouble with any of the softwares, then ask for help. There are plenty of people in the foundation who know how to do this. And possibly we could arrange some hands-on training, so in one-to-one or small groups. There's a link there for the source code of the slides if anyone wants those. I will be making these slides, this PDF available, and links are there as well. And legal stuff. That's it from me. Does anyone have any questions?
Awesome. Just a reminder that we'll be taking questions on the YouTube live stream and on the IRC Wikimedia office channel, and I'll go ahead and check those 2 venues right now. We have a few thank yous from folks, but right now we don't have any questions. I'll wait for a minute on the live stream, and then what we can do as well, I know the link was changed before the talk, and maybe folks will catch up with it later, is if people send questions, we're more than happy to get those to Lars to get them answered as well. you. Check my tweet. Okay, Lars, it looks like we don't have any questions at this time. So I want to thank you for coming and speaking with us. That was a really interesting talk, and I was kind of side channeling during it, and I was like, I would like to rename this talk "Kittens and Cryptography." The images are so cute. So thank you for joining us, and then thank you, Brendan, also for helping with AV. We'll be back next month with another talk.
Thanks.
Thank you.
Thank you.